I'm going to do now the tutorial about the cavity method. It's not supposed to be super long, so don't worry. And after that we take like a few minutes break and we do the preparation for the test. So we saw like some questions from last year test. Fun. Okay, so in the last tutorial we started to talk about spin glass model. So we introduced the Hamiltonian with the disorder in the coupling. So we have JJ, which is random coupling coefficient, sigma I, sigma J. Sigma can be plus minus 1, like Ising model. This is like a mean field type of Hamiltonian, so we have interaction between all of the spins in the system. And the coupling J has been taken from Gaussian distribution. So you assume that the first moment is 0 because everything is symmetric, and the second go as 1/n. So the last time we talked about quench disorder, we said the J is a quench. In the case of spin class, we talked about quench disorder because the disorder changed very slowly with time. So we assume it's frozen in time, and then we look at like different replica of the system and we compare the other parameters. A lot of fun. So what we're going to do now is a bit different. So to understand the concept of what we're going to do, let's remember what we used to do in regular mean field. But like, did you do type of mean field in like bachelor course statistical physics? With like Stas or something? You mentioned that or something? Never mind. Anyway, so let's do something like very, very simple. So let's say we have an Hamiltonian. So this is ferromagnet mean field. So we have an Hamiltonian where J is larger than 0. So this is the normal ferromagnetic Hamiltonian. And to solve this Hamiltonian, I define some kind of effective field. I called it HI, effective. And I said that this effective field is equal to J, and this is the sum of I and J, so this is sum over J. Let's say J is smaller than I or something, sigma J. So now I can rewrite the Hamiltonian as minus sum over I, HI effective, sigma I. Right? I didn't do anything, just rewrite. So now if I want to calculate so now I do the first assumption that I do is I take the average, I replace, the state of the spin sigma J with the average state of the spin. So this is the average of sigma J. I call it NJ. And now I want to calculate the average state under this assumption of the spin sigma I. So what this is going to be, so we have a sum over sigma I E minus beta H, so beta HI sigma I over sum of E beta HI sigma I. So this is like the partition function of the numerator. So sigma I equal to plus minus 1, right? And H is a constant because we assume that we take MJ to be the average. So this is just J MJ. So the effective field is just constant. Then this is we have positive and negative exponent here, and also here. So this is going to give us overall hyperbolic tangent So we have bunch of beta H effective. So this gives us overall that the average spin in the system, and because the system is all symmetric, so this is just the average spin in general, yeah? So the average spin, M, is equal to a parabolic tangent of beta H effective, which is what we wrote here, beta J M. So under this approximation, we found a self-consistent equation for the magnetization M. So you can solve that like numerically, you know, you plot both sides of the equation, you find solution for M. This is basically the equation that we got when we talked about like Sudden approximation in a bit longer way. But this is pretty easy to solve because everything is symmetric and nice. Okay, so now instead of using the ferromagnetic Hamiltonian, we're going to use the spin glass Hamiltonian. So what's going to change is basically here. I will do it in different time to compare. So now here we have J inside the Hamiltonian, and which means the effective field is sum over J of J sigma J. And now, because the system is no longer completely symmetric, like we have different couplings in the system, we cannot stack like the magnetization of the spin J and spin I to be necessarily the same. We have different like different state of the system through the of the spins through the system. So what we get eventually is that the magnetization of the spin I, the average of sigma I, is equal to the parabolic tangents of beta Jij Mj. Okay, so the only difference is that now Mj maintained the index because we don't have the symmetry in the system, and Jij is also a variable inside the sum. So, sorry. And all of that is inside an average because this is still a variable with respect to the probability of Jij. So if Jij is some, so this doesn't have to be like disordered system, right? Jij can be just function of distance or something, you know, like when we did like a long-range interaction. And if that function is known, so this is relatively easy to find, at least numerically. But if Jij is some random variable form distribution, this is really a bit more harder to calculate. And so basically, okay, so the first point, for the ferromagnetic system, if we have infinite range of interaction, so which is the assumption that we made, right? In the mean field, we assume that all of the spin interact with all of the spins, so we have infinite interactions. Then this approximation gives us exact solution under this, for this Hamiltonian. But for the case of the spin class, apparently this effective field, so we call it without the beta, this H effective, it's not good enough, it's not an exact solution of the system, and we need to add additional correction from the order of 1 over n. So, so what it turned out to be is that the magnetization here, maybe I should write it consistent with the notation. So mj is not the magnetization of the spin j, but the magnetization of the spin j in the absence of the spin I. So those are like different spin, and this summation run over all of the spins in the system, including the spin I. But this magnetization, if you, I don't know how they found it exactly, it sounds a bit hard, but eventually it's give the magnetization of the system if I remove this spin, which is kind of the assumption that we're going to make in a second when I talk about the cavity method. So what we need to do is basically just add an additional term to the system that we're going to find in a minute. So questions so far? Okay, so so this correction is called Onsinger correction, and we have we have few ways to find it. So one relatively straightforward way to find it is by adding fluctuations to the magnetization mj, and this is what we're going to do a bit more explicitly. And the second option is using the cavity method to calculate this expression, which I go through the outline of this a bit later. So let's start with that. So this assumption that we made, that we replace the state of the spin with the average state of the spin. What if instead of doing that, let's go back to the so instead of that, we take sigma j to be mj plus some correction. Right? So this is delta. It's relatively small because we assume we have small fluctuations around this average, but it is a correction. So let's see what it's going to give us. So now the effective field is equal to jj mj plus jj delta sigma j. So if we add it here inside where the effective field is supposed to be, we have the average of mi is equal to hyperbolic tangents, the average of hyperbolic tangents, beta jj mj plus beta jj delta sigma j. So now we need to see what we do. We want to see what we can do with this average, because the average is outside of the hyperbolic tangents, but we have the fluctuations inside. So this is a bit non-trivial calculation to do. So what we're going to do is we're going to expand using Taylor series the hyperbolic tangents and then divide it into different averages. So so in general, I will write a reminder. If we have hyperbolic tangents of x plus delta, where delta is the small parameter, then this is approximately hyperbolic tangents of x plus delta square, no, sorry, plus 1 minus x delta square minus delta. Minus delta square, 1 minus tangent square, multiply by tangent. Okay, so we expand the tangents inside the average into those three tangents, and then we average each one of them independently. So, so the first expression, this I'm going to call that part H average, because it's like the average field with respect to the state of the spin. So just to have a shortcut. So in the first order, Mi is equal to tangent of beta H, and to that, the contribution of the fluctuations I'm going to call eta, like fluctuation. So this is plus, let's put the average over everything, plus eta beta 1 minus tangent square beta H minus beta square eta square minus tangent. Okay, so the average over summation, I can take this the average of each term independently. So the first one, this is like the average field of the system. So the average of that is just that, right? This is just a constant for us. So this is equal to. So this is just remain tangent of beta H. So similarly here, this expression not going to be affected by the term average. So just the average. But I have linear dependence of fluctuation, but by first order we assume that this is going to be 0. Put it here. We assume that this is 0 because the system is symmetric. So we know that the first moment of j will be 0, and this part doesn't have any reason to break symmetry. So the first moment of the fluctuations will be 0. So everything that we have left is the second moment here. So this is going to give us contribution of minus beta square, average of eta square, and then just copy everything that's come after. Okay, so now we need to calculate beta square. So let's do it here. So eta square is basically the variance of the system, because what's the fluctuation of sigma is the difference between the spin to the average of the spin. So this is just sigma j minus mj, and if I write it explicitly, so I have average of spin J sigma j minus mj. So the first term is sigma square, which is just 1, right? Because sigma equal to plus minus 1. So sigma square is equal to 1. Then we have minus 2 sigma j mj plus mj squared. So we already assumed that the fluctuations are symmetric, right? So the average over the state of the spin, which fluctuates between plus and minus 1, is 0. So this is going to cancel out. And mj is the average state of the spin, so we can basically take it outside of the average. So this is just a constant. So what we are left with is jj square multiplied by 1 plus jj square multiplied by mj square, which we took outside of the average because it's a constant.
Why the second term is 0?
This?
Oh.
Why this cancel out?
Yes.
Because sigma j is plus minus 1 and the couplings, or the distribution of the coupling is symmetric. So the system, I didn't prove it, but because everything in the system is symmetric, we assume that overall the fluctuation average to 0.
And concept will be plus minus plus minus plus minus.
Yeah, sigma can be plus minus 1, and the interaction is equally can be plus minus 1, so overall in average everything is. Okay, so we said in the beginning, when we wrote the Hamiltonian, that the Gaussian distribution that provide the coupling, characterized by the second moments that go as that's equal to 1 over n. So each one of those we know equals 1 over n. So this is So this summation, I have summation of where j go from 1 to n. I have n spinning the system, so I have n multiplied by 1 over n from this. And here, like mj is constant with respect to the average, but I still have the summation over all of the different j's, so I have to leave it as a summation. So I have 1 over n sum over mj squared. So overall, this is equal to 1 and I think I'm supposed to have minus. I lost the minus somewhere. Just a second. Okay, I'm sorry, I lost a minus somewhere, but this should be overall equal to 1 minus q. So q is that summation, and I lost the minus on the way. So for now we'll leave it like that, and I will go back to about why do we have a minus. So this is for now at a square. I will look at that at the break. Okay, so we kind of calculated the second moment of the fluctuations, and now what we're left to do is, so what we originally wanted to do is to find a correction to the effective field. So now we have an equation that relates to mi. So we want to write all of that as function of the effective field, which means this is equal to hyperbolic tangents of some effective field H effective plus H effective star, which is the correction. So basically what we do, we use again the Taylor series that we started from, and we like reverse it. So we go from the right hand side to the left hand side, and if I want to write all of that in the form of that, so I can basically use the first order here. So if I say that delta is all of that, I can rewrite that as hyperbolic tangents of H average minus beta square eta square hyperbolic tangents of beta H. Okay, and now this is H effective plus H effective star. So this is the new effective field. So what we got here, basically you see that, okay, the first order is trivial, is what we got before, and here the hyperbolic tangents by first order, this is the magnetization mi, right? This is the first order of mi that we got before, and the second moment of eta is a correction that go like 1 over n. So so we got the correction that we were expected to find. So the meaning of this correction is basically like, so if we said initially that the magnetization in the average H, like this magnetization is the magnetization in the absence of mi. So the correction is like a feedback of the magnetization of mi on itself via the rest of the spins. Like, you know, like you have mi that respond to mj, and then you have mi that respond to mj that respond to mi. So it's like a second order correction of the interaction. Okay. Questions? Okay. So the cavity method. So basically, what the method say is that it's too complicated to look at, like, if we have this effective field. So what we did here, we took sigma j to be an average, but you have hidden correlations inside the system. So the method state is that instead of doing the approximation in that way, what we can do is we can take one spin and isolate it from the system. So we assume that we have n spins, sigma k, where k go from 1 to n, and we add one spin, sigma 0. So after the system arrives to equilibrium, so sigma k are in equilibrium with the rest of the sigma k, but not with sigma 0. Okay? So the equilibrium with different 0. So basically, we take the system and we add it. We add a new spin to the system, and then we see how the system, how this spin respond to the system in a way. So the reason people refer to it as cavity method because because what I actually do, I take off the spin from the system. So when I take off the spin from the system, the difference in the overall field is what they call the cavity field. So I create this like hole in the system. Okay, so why is that helpful? So we said that all of those, if I want to look at the different contribution of the fields as random variables, they're all correlated to each other. So that's a bit harder to do. So what I do, I look at this specific spin after everyone got to equilibrium, and then the effective field of the spin 0, let's call it that. So it's J0 J sigma J. So we now add those couplings to the system, but the different spins in the system are already in equilibrium. So we assume that they are already in equilibrium, which means that they're not correlated to the new state that we added. It's a bit weird, but yeah. So why is that good? Because now we can say that because the different J's they be taken from Gaussian distribution, which actually work even if they're taken from other distribution, but it's just simpler. So we have the sum of IID variables, which means that we can use the center limit theorem. So the summation of all of those random variables is going to give us Gaussian. So P of H is like a Gaussian, like this n that represents like a Gaussian distribution with average of 0 and standard deviation of, no, we can't use sigma, we already have sigma. Forget about that. Just Gaussian. Okay, so the parameters of the Gaussian, the Gaussian defined from with average and with variance. So the average, which is, we call it, okay, let's stay with H bar as earlier. So this is would be actually the effect that we defined here. So this is the contribution of all of the different spins of the system. Just want to check the system with the water itself.
P of H, it's distribution of this average field.
This is the distribution of, no, so, okay, let's, this is average, and this is average, and this is the field in general, the value of the field. This is the average field, this is the value of the field. So here I put average over the different states spin, and so this will be the actual H. Yeah. So one is with average, one is without average. Okay, so this definition is basically similar to what we did before, except that now we only look at the contribution at the spin for I equals 0. So, okay, so because we allowed all of the rest of the spin to get into equilibrium, when we do the full calculation, we don't have to account for the contribution of the energy. So if we have, like, you know, the Boltzmann weight, when we do the partition function and everything, we don't have to account for the different spins of all of the different spins, but only for the change of the spin of sigma 0, because it's the only one that didn't get to equilibrium yet. So, okay, so we have the distribution of the field, and basically, what we do is we say that we can define a distribution, call it like capital P, that is a distribution. So I'm not going to do the full derivation of that because it's like half of the book, but the outline is that we define a distribution for the value of the field and the value of sigma 0, because those are the only parameters that we have in the system, because we said that everyone else goes to equilibrium. And this distribution is basically relates to the Gaussian, it's basically multiplication eventually. You can prove it. It's the Gaussian distribution of the original field. So this is the field, just the value of the field. So let's call it, I don't want to call them both. Okay, so this is PG, so Gaussian. H, and the probability distribution for the spin, which is just the Boltzmann weight. So this is E beta, J, beta, H, sigma 0. So this is the Boltzmann weight is E minus beta multiplied with the energy, right? And the contribution of the energy here is the contribution of the interaction with all of the fields. So H0, which is a Hamiltonian of sigma 0, is J0J, sigma 0, sigma J, right? The interaction with all of the rest of the spins. So this is equal to H, which is the random field that we define, so H0, sigma 0. So this is the same H as we have here. So that thing over here is going to give us the distribution of the field. So, okay, so this is probability of H for n spins. So this is without I equals 0, and this is the probability for n plus 1 spins. So this is after the distribution, after we add one additional spin. So with sigma 0. Okay, so basically what the concept of all of this method is that we have a bunch of spins that we know the states, which are all of the n spins before, and they have this simple distribution for the values of the field, because they're already roughly equilibrium, so they're IID. And what we do is each time we supposedly just introduce one single spin to the system that can change its state. So the new distribution is just going to be affected by this single spin. So we have one introduced new variable, which is sigma 0. So what's going to happen now is that if now I'm going to so the way this is similar to what we did before is that we say, okay, we take all of the spins to be the average state of the spin, and we introduce some fluctuation. So earlier we just say, okay, we have fluctuation for all of the different states of the spin, and here we said that the fluctuation arises from the spin that we are looking at. So in that case it's sigma 0, but 0 is just an index. So we have additional contribution from the one spin that we measure. So if we take this distribution and we calculate the average value of sigma 0, what we're going to get, so we have the summation over sigma 0 that equal to plus minus 1, and we have the average over the probability distribution. So this is function of h and sigma 0 multiplied by sigma 0. Right, this is just normal average, and if you will do that, you get that this is equal to a parabolic tangent of beta h average. So this distribution, of course, depends on the average, right? You have Gaussian shift, and then what you get eventually is that's the first order solution for sigma 0. So I call it, okay, no, I don't call it. I just leave it like that. Okay, so if I calculate now the average value of h, so notice that this average value of h is not this average value of h, because this value is where the state of the spins are for n spins, so let's call it hn, and this is for n plus 1, because we calculated with respect to the probability distribution of n plus 1 spins. So what this is going to give us is that this is equal to h for n spins plus hyperbolic tangents of beta h 1 minus q. I don't know if I mentioned that, but no, I didn't mention that. Okay, I will write it in a second, but for now q is the q that we defined before. And let's say that I didn't forget anything. And beta, of course, and beta. So this is similar to what we said before. The variance of the field is equal to 1 minus q. So this is the way 1 minus q found its way to the probability distribution. But we don't really care about that, but this is just a given distribution, and this is the result that we are getting from the integral. Okay, we're almost done. So by first order, we found that the average spin is defined by the average magnetic field, and then if you calculate the average magnetic field, we get this this correction. And we said earlier that this is just average sigma 0. So from that, the next order is that sigma 0 for the n+1 system is the hyperbolic tangent of H effective, where H effective is equal to H minus beta 1 minus Q sigma 0. So once again, we got the self-consistent equation for sigma 0, where this is the exact correction that we got from the Taylor expansion earlier, where Q is 1 over n sum of sigma j squared. So this is the dependence on the rest of the spin. This is the 1 over n order that we expected for the correction, and that's basically it. This is. Okay, notice that here we had this is equal to that, and I replace I subtract the thing. So I have Hn equal to that minus that. So this is how I got the minus here. Okay, and this is the overall solution of the spin class by this method, and those like two sets of equations are also called tap equations after 3 prepared. The name delta steps. I think this is Anderson. Okay, so this is cavity. Super fun. If you want to look at like the actual derivation, you can look at the book. I don't recommend, but you can do it. So, do you have questions? And
so it's an iterative transformation. You're like doing it each time, add another spin. Not really adding, but
no, because here, not exactly, because here we looked. The point is that the additional contribution, the correction, came from the specific spin that we look at here. So the self-consistent is for sigma 0, and the correction relates to the rest of the spins, and so I can choose whatever spin I want. I can do something similar and continue, but then I get like additional orders. I think you can do it for more orders. I don't know how to do this, but you could do something similar. But yeah, that's basically the. Okay, so if you don't have. Okay, so I'm going to solve the moed email of last year. Maybe I'll change some stuff. We'll see how much time we have and how tired we'll be, and whatever I'm not going to have enough time to do, can put in the model. So it's up to you. Okay, so the first question. So given one-dimensional Ising model, with interaction between the different spins, Gm. So M is like the distance between the different spins. So M is like 1, 2. So we have actually J of M. Okay, never mind. Let's just stick to the way the equation is written. Okay, so we have one-dimensionalized model with coupling J as function of the distance, and the question is which one of the systems, let's write this too, which system which of the systems goes through a second order phase transition. So we solved like a bunch of questions like that during the course. Mostly in the tutorial we talked about phase transition. So basically we have a coupling that's function of the distance, so we know this is going to be related to long range interaction. Right? You can have phase transition in a few different scenarios. So if we have like a higher dimension, so this is d equal 1, so it's not the case. And if we have long range interaction, so this is clearly that. So the options are, let's do it one by one. So the first is J of M equal to E minus M to the power 0.11, or not 11, just 1, 11. So 0.1 over N. So, just a reminder, we have phase transition for J of M that go as M to minus sigma if sigma is smaller or equal to 2, which means that the interaction in the long range is strong enough, so we can keep the correlation. So what we want to do is to check how does function decay for large values of M, and if it's faster or slower than M2 to minus 2, then we know if we have phase transition or not. So the easiest way to do that, I think, because not always it's very easy to take like the to expand that like a Taylor series for large M. So the easiest way to do it is to multiply it by M squared and see if you get something that goes to 0 to infinity, right? So let's do it here. So we want to take this expression, and in the limit of sphere of M go to infinity, if that expression, if it's go to 0, it means that this decay faster than M to minus 2, then there is no phase transition. There is phase transition. There is no. There is no phase transition. And if it goes to infinity, there is phase transition. Okay. So yeah. Okay, so how would you do that? So in that case, we have, so the limit that we have is basically M over, it's a bit easier to write it like that, M over an exponent minus plus M to 0.1. And we see that both of those going to go to infinity, where we take M to infinity. So what we can do is use L'Hopital. Remember L'Hopital? So, I don't know if I know how to write L'Hopital. I think it's something weird like that. Something like that.
Can we just say that exponent grows much faster than any
Yes,
linear?
you can.
Or
I just want to show a method for cases that you can't say that. I'm just doing the long way around. But yeah, you can definitely just say, oh, this will go faster.
Yeah.
For sure. Just add in as many extra steps, of course, as possible. But no, yeah, we do it once. We don't have to do it for every time. So okay, so we do L'Hopital. So we take the derivative. If you remember L'Hopital, we take the derivative of the denominator and denominator, and you compare them after derivative. So this is going to be 1, and this is going to be 0.1. So the exponent state goes to infinity, all of that go to 0, and as you said before we already did it, we don't have any phase transition because the exponent clearly go to 0 much faster than anything that we're going to multiply. And this is basically like the rule that you can use always. Anything that you have with an exponential decay, doesn't matter what we have inside this exponential decay, going to be faster no matter what I multiply this with. So the only thing is that we need to make sure that this is really an exponential decay, because sometimes you don't like to give stuff that are like log of your cos of an exponent of like weird stuff. So yeah. So this is 1. So no phase transition. Number 2. So j of m is equal to m to 0.5 over 1 plus m 2.25. So where m go to infinity, the 1 is negligible. So this is basically just m to minus 1.75, and this is basically sigma equal to 1.75, and we immediately can see that this is smaller than 2, so everything's great. We have phase transition. For 3, we have j of m equal to e minus m over m. So this is like over m cube. So this is very similar to what we initially did. If we multiply that by m squared, this is 8 minus m over m. And again, even that we still divided by m, the exponents decay much faster. So the 1 over m just make it decay even faster than the exponent. So we clearly don't care about that. So this is equal to 0, and so no phase transition. Number 4. So now we have an exponent of minus m to 0.1 over 5 log of m. So super fun. Yeah. Okay, so there are 2 points here. You may see it immediately, but if you're not, any like power of m that we're going to take would be faster than the logarithm. So what I have inside the exponent, like this argument go to infinity, just go to infinity as basically like the power of m. Like this is going to dominate when we take m to infinity. So everything I have here is still going to behave like an exponential decay, and you can do something similar to what we did here to show it with a few extra steps. But you know, everything that's going to be inside an exponential, you can see from here that when I continue to take derivatives, the exponential are always going to stay. So it doesn't matter what I multiply it by, this is always going to be constant, and the exponential is always going to be an exponential. So when I multiply it by m squared, this is still going to go to 0. Okay, so exponential decay, there's no phase transition, even that I have this log here because it still multiply the m to 0.1. So number 5 is hyperbolic sine function. So we have sinh of 8 log of m to 0.11. Yeah. So okay, so this is, we can rewrite it as 2 exponents. So this is basically e to the power 8 log m to the power 0.11 plus minus, sorry, e to minus 8 log same. When I take m to infinity, the second decaying exponent is going to go to 0, so we can neglect it with respect to compared to the first one. And this is basically, okay, you can see it immediately, but this is basically something that's go like, let's go like m to 0.11, so this is not even like, it doesn't even decay, it just, yeah.
M to 0.88, no? Because you take the 8 inside the logarithm.
Sorry?
Shouldn't you take the 8 inside the logarithm?
Okay, and the last one for normalization. Last one is
But why?
Hmm?
Why there is no phase transition?
Because it's not time frame square. It's just integer. So it's minus. No, right.
It's minus or?
No. It's
no,
smaller than 2.
sorry.
It grows actually.
It's
so-
positive. It's positive.
Yeah.
Okay.
I'm sorry, 2 tutorials in a row. It's too much. I'm sure for you too. But yeah, it's positive. It's explode. This is like highly not a physical thing, but from technical point of view, yeah, it's explode. It's definitely decay slower than something decay, because it doesn't decay. So you do have it. Okay, let's okay. So last one. So j of m is equal to the hyperbolic tangent of e to the power m. So this is equal to, we can rewrite it as e to n minus e to minus m, e to n plus e to minus m. So it's the same
To the e term?
e to the e, because
Just goes like 1.
so yeah, so those two decay to 0 so fast, and then yeah, we just stay with something that's proportional to 1. So yeah, this doesn't decay. This is the same case as number 5 basically. It doesn't explode, but yeah, just a constant, so you do have phase transition. Okay, so this is basically pretty easy type of question. You just need to be focused. But yeah. Questions? No? Oh.
So if it goes to a constant, it still have phase transition to a non-zero constant?
Yeah, because it's decays slower down. Yeah, it's like imagine if you have a system of spins and they're all correlated like so strong, so if you flip one of them, like everyone's just going to follow.
The behavior of the last one system is like mean field. Like all spin in some constant.
Yeah. Exactly.
Environments.
Okay, so that's the same test, question 2. So you're given a two-dimensional Ising model. This is also a phase transition question. And now it's anti-ferromagnets. So you have like two-dimensional grid. So the Hamiltonian is sigma I j sigma I plus 1 j and sigma I j sigma I with j plus 1. So either go on x or y x. So first of all, find the configuration of the spins in 0 temperatures. So if we have 0 temperature, we don't have fluctuation, so everything goes to the ground state. If we had ferromagnets, then it would be trivial, all of the spins go either up or down. But here we have anti-ferromagnets, so it's going to be something like that. So if I have a spin here that's up, the next one next to it is going to be down. Let's do it with coral. So this is plus and this is minus. This is minus, etc. And also on that axis, if this is 1 plus, then this is minus, plus, minus, plus.
So there is no frustration here.
Yes. We don't have frustration because we don't have like loops with 3 spins. This is like 2D grid, so everything's fine. If we have like a triangle type of grid, so yeah, it will be all different question. So this is the configuration. They didn't ask here about the generality for some reason, but if they ask about the generality, so clearly the generality here is similar to the ferromagnet one. We can flip all of the spins, so we have the generality of 2, right? The two states that are completely equivalent. So the second question is to define an order parameter. So if we usually have the order parameter that is just a summation over the different states of the spin. So okay, define order parameter that is equal to plus minus 1 at 0 temperature, and equal to 0 where the temperature go to infinity. So in normal ferromagnet we have either everyone up and then it would be plus, or everyone down and it would be minus. And when we took t equal to infinity, then half of them up and half of them down. Like everything is completely random, and then the order parameter is 0. So we want to define something similar here. So let's call it R to Q. So we saw that in 0 temperature, we have like exchange between the different indices, so they go from plus 2 to minus 1. So, and if we flip them, and the other option is every one of it. So we can define a summation, but instead of just take the state Si, we take Si multiplied by minus 1. Sorry, Sij, we're in 2D, so we have minus 1, I plus j. So when we go through the different sides of the system, so we're going to flip, this is going to flip between plus and minus 1. So because Sij also going to go between plus and minus 1, so when we're going to sum over that, it's going to be either everything plus or everything minus under such configuration. When we take the temperature to go to infinity, then actually what's going to happen is that almost all of the spin is going to go to the same direction, either everyone up or everyone down, and then that's going to be 0 because this is constant, and then we just switch from plus to minus 1.
Shouldn't we have a normalization like 1 over n, something like that?
For sure. Okay, then I think it's the last one. So we add a weak magnetic field. That is equal to plus minus epsilon, where epsilon is much smaller compared to the coupling J. And the question is the system going to undergo finite temperature second order phase transition? So what do you think? Does look familiar. So when we talked about weak magnetic field, we talked about the Imrim argument. So remember, in the Imrim argument, what we did, we had like we did in ferromagnets, but it can be easy like translated to a antiferromagnet. We just do this transformation. So we have the contribution of the energy from the field. So we had like a bulk, and we had like the boundary of the bulk. So you have the contribution of the energy to the energy from the difference of the field, and we have the contribution to the energy from the coupling. So if we have if you have like the pluses here, and we have the minuses here. So we have this. So this is going to give us like in the ferromagnet, it's going to give us like one contribution of the energy from the shell and the other contribution of the energy from flipping the spin with respect to the effect of the magnetic field. And when we compare those, we found out that the weak magnetic field only going to destroy the phase transition, to prevent the phase transition where the dimension is equal to 2, right? So from the Imbrima,
Equal or less?
yeah, but for less we don't have phase transition anyway.
Yeah.
So for Imbrima, we have no phase transition for weak magnetic field. Under the condition that the average magnetic field is 0, we don't need it here, but it's an important condition. For d smaller or equal to 2, yeah. Which is actually only translate to be equal to 2 because for d smaller than 2 we don't have phase transition to begin with. So we remember that this is the Imbrima argument, and which means that in our case, because we work in dimension 2, so we don't have phase transition because this is the exact dimension where the magnetic field won't phase transition. So no phase transition. And in the context of like a test, you can just use that. You can just write that Imbrima argument works for that dimension, and that's enough, like explanation. So if we work the dimension larger than 2, so we needed to take into account the average of the field. There are a lot of like questions of that type, and in that case it's easier because it's plus minus epsilon. I don't know if it's in the question, but probability half. So the average is 0, and so if we had like a 3-dimensional system, so we did have phase transition. And we needed to state that the average is 0, and therefore we have phase transition. But because we don't work we work in the equal 2, so none of that even matters.
So it doesn't matter if it's ferromagnet or antiferromagnet.
Yes, because
Same.
you can do like a transformation between them.
תחזרי על השלישי. במימד גבוה.
So for dimension that larger than 2, the magnetic field don't ruin the phase transition.
Right.
So we can have phase transition in the with the existence of magnetic field if this is true. So that's the condition for the Imbrima. There are two conditions for the Imbrima argument. One, the average is 0, and the other one is that the magnetic field is weak. And weak is of course compared to the coupling. So this is an other scale that we have.
Okay. If it's a strong magnetic field, it's not a... And if it's strong magnetic field?
If it's strong magnetic field, we don't have phase transition anyway for that type of you have system with phase transition and you find a magnetic field, but it's like it's something else. It's not you can have you also have it for the spin glass. You know this diagram that you have like temperature, something like temperature and a magnetic field, and you have like something like that, like order and disorder. But yes, as far as it's concerned, this is not what we talk about here.
Could be epsilon not discrete value, continuous one. For example, I don't know, normal epsilon is normal distributed, and it has
It's
zero
taken
average.
from something continuous. That's what you said. You have value of epsilon for each site in the grid.
Yes.
So you mean that the distribution is not discrete?
Yes.
yeah, so it's be taken from continuous distribution, then yeah, if you need to calculate the average for the distribution.
If it's 0, we can use
Yes.
minimum argument.
Yeah, so if it's like Gaussian, it's
Yes.
around 0, so yeah, it's still valid. Never saw you do use that for some reason, but yeah, it will be fun. Thanks for the idea. Okay, so I think that was the question. And there we go. So last question is, yeah, the last question is a bit, I think we either solved that or something that's identical to that a few tutorials ago. So about question from Moed Aleph of last year, which I think is a bit more fun. So let's do that. So this is Landau theory, and so this is again 2024 a question. So given the free energy around the critical temperature T0, so okay, let's write this. Around T criti, not T0. So around the phase transition point. So f is equal a of t m to the power n plus b m to the power k plus c m to the power m, so m in capital M, minus h m to the power p. And it's given that n is smaller than k is smaller than m.
AT goes as T.
Yes, and a of t go as t minus t criti, which is t. So this condition just tells us that those are the leading orders by the order that we use to write them. So this is the smaller one. And the question is find, if possible, n, k, m, and p as function of the critical exponent, which are alpha, beta, gamma, delta. Okay, so yeah, so very important point here is that. So we actually kind of solved this question in the tutorials because we found we already know how to find those exponents when we have specific numbers here. So now we're just going to find them as a function of those like unknown numbers, and then find the inverse of those solutions. So it's actually not very bad. Okay, so let's start with our favorite, which is beta, which is the critical exponent of the magnetization with respect to the temperature. M, T. Okay, so what we want to do is we want to find a magnetization at the critical point, which means that we want to minimize the free energy, which means that we take the derivative and compare it to 0, right? So df over dm, and we take the field h to 0, and later we do the opposite, we take t to 0 when we look at the exponent with h. So this is equal to a of t n mn minus 1 plus b n n k, sorry, this is k, k and k minus 1, and this is going to cancel out, and plus something of order of m to n minus 1, which I'm already ignoring from because I know that it's going to be the highest order. So I'm only going to take always the two leading orders. Okay, so and since I was told that m is the largest number here, I'm going to ignore it. And all of that is equal to 0. So this is approximately going to be equal to t. And I'm going to ignore for now to the end of the question all of the coefficients. So everything that multiply like n, b, and k, because we look at the order of m. Okay, so I'm just going to ignore any coefficient. So this gives us t m n minus 1 is approximately equal to m k minus 1 with minus. So this is, just continue. So this leaves us with m k minus n approximately minus t, so m is t 1 over k minus n. So beta, and I'll write it in the corner so we get it for later. Right. So beta is equal to 1 over k minus n.
So after we find out all of the exponents, we just check if it's consistent with scaling relationship. No?
Yeah, we can use this. Okay, we can use the scaling relation to. So we can use the scaling relation as like a sanity check.
Yes.
After we find everything
If
to
it's
check that
satisfied or
everything.
not.
Yeah, to see that everything that we got is right. If we are out of time or lazy, we can use the scaling relation as after we find two exponents to find the third exponent. So you can both. You can go either way. Depends on how much time and patience we have in the test. But yeah, both ways work. Okay, so we found beta. Let's go to delta. So m go as h to 1 over delta. So we do the exact same thing, but now when we take the derivative with respect to n, we take the reduced temperature T to be 0, which means that the temperature is equal to the critical temperature. Okay, so the first term that relate to A of t. So because this is proportional to t, this is going to go to 0, or we take t equals 0, so I'm already ignoring it. The second order going to come from b, so this is going to be b, k, and k minus 1, so this is similar to before. And after that we have those two orders. So the last term, which h, I have to keep it because that's dependent on the field that I want to find eventually. So this is going to give me another order with m, and then again this expression going to give me higher order of magnetization just higher order of normalization, so because we take m2 to 0, I can again ignore it. So what I'm going to be left with is h, p, m, t minus 1. So you can already start to see that we're going to have a problem with that parameter. Okay, so again, ignoring all of the factors, we get mk minus 1 equal to h and p minus 1. So mk minus p equal to h. Therefore, m go as h 1 over k minus p. Is that right? Delta equal to 1 k minus h.
No, it's 1 over delta, right?
Yeah, just
Yeah.
k minus p.
Yeah, this is one of them, of course. Okay, let's go to alpha. So alpha is for the specific heat, so CV go as T2 minus alpha. And okay, I think here we can do the okay, so the specific heat basically related to the second derivative of F with the temperature. So what we're going to do, if you remember, we don't have the free energy as a function of the temperature, but we have the free energy as a function of m, and we have m as a function of the temperature. So we're going to take, we're going to write f as a function of t, and then take the derivative. So this is approximately so this is linear of t, and then m to the power n. We found that, we already found that m proportional to t to 1 over k minus n. So we just multiply it by n. So this is 1 plus n k minus n. And then the second order, so this is plus. So this is t to k n minus k, which is actually going to give me the same order. And then something that's going to be of order of t to m n minus k, which I know it's larger than those, so ignore it. And the last expression, we can take the field to be 0, so it's going to cancel out. So you see this is also equal to k minus n. So eventually the second derivative is going to be t to k minus n minus 2. So just leave it like that for now. And which means that alpha is equal to 2 minus k minus n, or we can write it as, so we have 2k minus k, so we have k minus plus 2n k minus n. So this is that. think it's okay. Let's...
זה לא יכול להיות שהאיבר השני, האמצעי הוא הדומיננטי, כי המחנה שלו קטן יותר?
This
לא,
one?
האמצעי.
Yeah, but they're the same because I have 1 plus that. So this is actually k minus n plus n over k minus n. So this is
לא, אבל אחד הוא מינוס של השני.
Yeah, this is because I made a mistake. So k minus n, yeah.
Why it's k plus 2n, not minus 2n?
Because yeah, that's the mistake I'm looking for, but so this is okay. Yeah, this is okay, yeah. That's okay.
Shouldn't be k plus 10.
Minus 2.
Minus.
Okay, yeah, that was a mistake I was looking for. Thank you. Okay. Now, technically, we have one more exponent to find, but let's stop for a second and see what we have.
We have the scaling relation.
Right? We also have, so far we have 3 equations with 3 variables, right? We have alpha, beta, and delta, and they're all function of k, and this should be p. I don't know why I put that p. K, p, and n. But we don't have anything that depend on m. So basically, we can use those to find the three exponent that we're looking for, except of m. So the question is, are we going to be able to find m? And the answer is, you can calculate the fourth exponent and see that it's not going to depend on m. And you can also just see that every time we do calculation, we're only going to consider the 2 leading orders. And because we have this like extra unnecessary order here, we never will be able to find m directly from those exponents, because those exponents are only going to describe the behavior of the system as close as possible to the phase transition point. So any additional orders that we have here are not going to be included here. So even if we find gamma, which you can do in your free time if you want, you're going to see that it doesn't depend on m as well. So this is why the if possible part in the question is so important, because you just cannot find it.
It's pretty obvious because you don't have 4 equations. You have only 3 because of the scaling relation. You don't have 4 independent equations.
Yes. Yeah, also that, but it just physically impossible, because it describes something that happened like too far supposedly from the phase transition point, so it's just not going to affect the critical behavior of the system. But as far as it's concerned to you, yeah, you can just find gamma. It's 1 minute and see it. Just okay. So we have everything that we could use, and everything that's left to do is to inverse the equation. So let's just do that. So we have alpha. And we have those two. I didn't write anything about that, but fine. So, okay, so I'm just, do you mind if I just write the final answer? And you need to play a bit with the equations and basically get that n is equal to 1 minus alpha over beta, k is equal to 2 minus alpha over beta, and p is equal to 2 minus alpha over beta minus delta. That's basically it. Okay, so let's do one more quick question, and then go home. Questions about what we did here? No?
So why everybody write this third term in expansion of free energy?
Very
and if
good
we
question.
don't use it?
Yeah. So okay. So what happened? It's kind of okay. It's kind of related to now. So you don't need it to find the critical exponent. You can use it for other stuff. Basically, we can calculate stuff that are not necessarily the critical exponent. You can take as many orders as you want, and just get better description of free energy. But for example, if the order of this term will be an odd number, then you don't have second order phase position. But if you assume that everything is right, is like working in the system, you have second order phase position, and everything's fine. Yeah, you basically don't need it for any of those stuff. Okay, so the last question is kind of usually be given as like a second part to this question, but like not specifically in that test because this question is a bit longer. But if you have something with numbers, so that will be given as the second part. So this is from 2023. Question 2. So you have a series of examples for the free energy, the expansions of free energy, and for each one of them you want to determine if you have or don't have a second order phase position. So first, we have a of t, m to the power 4, b m to the power 6, plus c m to the power 19, which is just related to what we just said. Okay, so a of t is always proportional to t, and so we have a few conditions for the phase position, as we talked about it when we talked about random theory. So one of them is the leading order with the order parameter will change sign when we go below and above the phase transition. So this is what relates to a of t. That's why a of t is always proportional to t, because t relates to t minus tc. So when we go above and below it, this number is going to change the sign. So this works here. Okay. Another thing is that we only want to have an even orders of normalization, and the like different reasons depend on the term that we're looking on. But we see that here we have an odd exponent of m. So if we look at if we're trying to plot this expression versus normalization, so we get something that like. So if we usually have something that look like that above the critical point, and then like that, imagine it's symmetric below the critical point. So because of that odd expression, this is going to like drag down all of the negative numbers. So this is going to be something like properly, but you understand. This is going to go to minus infinity in the same way that this goes to infinity. So instead of having like two symmetric minima, you just have something to go to minus infinity, and this is clearly not similar to anything that you want to see here.
And it doesn't matter that it's like the highest exponent?
Yes, because if that was like an even number, then it's not going to affect too much the general shape of the distribution. But because it's odd, it's have like a...
I get it, but practically speaking, like the highest the exponents were like we neglect it in the other calculations.
That's why I said earlier, we only neglect it if we know that like if we already know that we have second order phase transition in the system. So technically we have to check all of those orders to see what we have, but yeah, because this is the last order, so it's described the largest value of m. So we don't care usually about the largest value of m because we look around m equal to 0.
Okay.
But if the large values of m behave funny, then we do care about them because none of our assumption works anymore.
Okay.
So really not phase transition. Number 2. So this is f equal to a of t, n to the power 5. Then b, m to the power 6, and m to the power 8.
So the same thing.
So yeah, the same thing, but it's going to yeah, so it's the same thing in the sense of it's going to break the symmetry. It's not going to look the same because this is affect again the smaller values of m. So it's not going to give me a convergence point, but it's going to give me something that look like so if I go below the critical temperature, maybe something like that. Okay, I don't know how to draw it very good, but something like that. Anyway, more or less. The point is that you switch from I put it on the model. I did like a real plot here. So the point is that you switch from one minimum to another instead of one minimum to two symmetric minimums. So this is more like a first order phase transition actually. But it's still the question is about second order. So this is still not true. Okay, the third one is f equal a of t square multiplied by m square plus v square m to the power 6 plus c m to the power, so this is m to the power 4, and this is m to the power 6. So all of the orders of m are even, but also the order of a of t is even, which means that this is now proportional to t minus tc to the power 2. So yeah, so if we go below or above the critical temperature, the system not going to change. So if I'm going to look at that, I have something that like starts like that, and then the critical temperature is going to be like that, and then above the critical temperature, it's going to go back to this. So we're just changing the y of the wall, but we're never going to have two walls. So no change in sign, no phase transition. And the last one. So now we have f equal a of t cube m square plus b m 8 to the power 8 plus c m to the power 10. So just roll a guess. It's 50-50. So all of the powers of m are fine, right? And this is the power 3. So what does it mean? It means that you have something that go as t minus tc multiplied by some function of the temperature, right? It's multiplied by t minus tc squared, which is a function of the temperature, but not something that affects too much the behavior of the system. It's a known number, so it's going to fluctuate a bit the width of the system, but fine. It's like it's a coefficient, so it doesn't really going to affect too much because this is still going to change sign when we go above and below TC, so we don't mind about that. So we do have a transition, everything is great. That's it. So this is the only thing. Okay, questions about the test? Something?
Can you bring
yeah, I need to send email about that. You ask me to do that. So in the test you can bring integral book and you can bring calculator, and that's it. And not a calculator that is in your phone if you thought about doing that, because it's not only to say that. So if you're planning on doing that, don't.
What do you mean by integral book?
It means that he thinks it's funny.
It's
a joke. He thinks it's funny.
I don't. Yeah. I don't know if it's like a funny thing, but if you have book of integral, I think it's used to be a standard thing like 50 years ago or something, and professors just keep writing that in tests. But I never saw anyone who made that. I think David Kessler had one at some point, but yeah, I don't. It's basically we don't have any separate calculator for practical. But yeah, but you don't have really a lot of equations, a lot of formulas to remember, and I think it's kind of good in some way, because if you assume that you don't have any formulas, so part of the difficulty of the question is to remember the formula, which is so yeah.
תודה רבה.
תודה רבה.